Once we begin adding substituents to a cyclohexane chair, and we'll use the methyl group as a simple example, we start to introduce some strain depending on the configuration of the ring. Here you can see our methyl group is in an axial position, and on the right side our methyl group is equatorial. And these two rings simply represent a chair flip or ring flip of each other. By having the methyl group in the axial position, we introduce some steric interference you can see between the methyl group and the hydrogens. This is called 1,3-diaxial strain because the positioning of the methyl group and the hydrogens they're interacting with are on carbons 1 and 3 respectively. So if we counted from the position that bore our methyl group, we call that carbon 1 and this 2, that would be the third position, or if we went in the back side of the ring, this would be 1, 2, and 3. So in this case, there's actually two 1,3-diaxial interactions occurring. When we consider the ring flip version, where the methyl group is equatorial, we lose the 1,3-diaxial strain. So between these two ring flip conformations, there's an energetic preference for the equatorial substituent. Here's simply just another view of the electronic space that the methyl group takes up. So what we're looking at is a space-filling diagram. So this outline here shows the electronic space that the atoms or groups require. And now you can see kind of the large area here that these hydrogens take up, and also the excessively large area the methyl group takes up. And indeed, they're interacting with each other here. And so that is the basis for the diaxial strain. This is the same molecule, just simply rotated around a little bit, just to give you another view. By looking at the Newman projection of the axial methyl group substituent, we can see a correlation between this and our example of butane in our prior set of slides. Here, this methyl group on position 1 is having a diaxial interaction between the hydrogen on carbon 3 and the hydrogen on carbon 5. And so in the top example, it's showing that Gauss interaction with 3, and here it's showing it with 5. And if we look over then on the right side at the comparative Newman projections, you can now identify that there indeed is a 60-degree dihedral angle here and another 60-degree dihedral angle here. We define that as a Gauss interaction. Here we can look at the equatorial substituted methyl group, and we see that we have no diaxial interactions. These hydrogens are just too small to interact with each other on the top or the bottom. But the methyl group on the side here and the perimeter lacks that interaction. And again, on the right side, we're looking at the same molecule, just turned a little bit. Here's a Newman projection, so we might be able to compare this to our butane model. And if we look at the interaction, for example, between the methyl group on carbon 1 and the group that's in position 3, this is an anti-orientation. And when we had butane, when we had the example for butane, there was no interaction between anti-substituents. So the equatorial methyl group is far preferred. So when we consider the ring flip of methyl cyclohexane, we've already stated that the preferred conformation is the equatorial methyl group. When the methyl is in the axial position, we have two 1,3-diaxial interactions between the methyl group and a hydrogen, and each of them costs 3.8 kilojoules per mole of energy, which adds up to a total of 7.6 kilojoules per mole of strain. Based on the preference for the equatorial methyl group, at equilibrium we can see that 95% of methyl cyclohexane exists in the equatorial position, whereas only 5% of the molecule exists in the axial position. And that's because of the 7.8 kilojoule per mole energy difference between these two conformations. Here's that number, 3.8 kilojoules per mole, and that is the interaction between a methyl group and a hydrogen. You can see that up here in the drawing. So each of these in this table represent the energy strain value between the hydrogen in an axial position and that particular substituent. As the size of the substituent grows, it's no surprise, for example, in the tertiary butyl group, to see that the energy strain is very large. And essentially, when you have a large group like that on a cyclohexane, you can nearly suggest that the molecule is locked with that group in the equatorial position. Let's work through this problem here where we're asked to draw the most stable chair conformation of 1,2,4-dimethylcyclohexane. We're going to have to do a chair flip then to answer the next part, which is to calculate the difference in energy between the two conformations. So we should begin by drawing a chair. Here's one here. And if you've never drawn substituents on a chair, when the groups are coming towards you like this, the easiest way to do this is to draw the substituents on the top side of the ring. If the substituents were on the back side, designated by a dashed bond, you'd put them on the bottom side of the ring. Also, when I have a substituent at the top or bottom of the ring like this, I tend to number this as 1, 2, 3, and 4. And so on my chair then, this becomes 1, 2, 3, and 4. So as we add the methyl groups, our first methyl group on position 1 is up in the axial position. And our methyl group in position 2 is up and equatorial. Our methyl group in position 4 is also up and equatorial. Before we do much analysis, let's go ahead and draw that chair flip. So my new chair is going to have this sort of geometry. We'll number our carbons 1, 2, 3, and 4. And remember, when you're drawing these chair flips, all substituents that were axial become equatorial, and vice versa. And then on position 4, my methyl's up here, and the hydrogen's down. So in both conformations, it looks like I can have some axial methyl groups, and there's also a couple of them that are equatorial. On the left structure, I'm going to draw a hydrogen here and here. It's not very straight, but that represents the diaxial interaction that's occurring between this methyl group and these two hydrogens. So I'm definitely going to have one of those, or two of those interactions. Also, the methyl group in position 1 and the methyl group in position 2 are at a 60-degree dihedral angle. You'd know that if you looked at the Newman projection along this line. And the methyl group in position 4 is equatorial, and it's not close to the other groups, so there's no interactions there. So I'm thinking we're going to need to add 2 methyl hydrogen diaxial interactions. That's 2 times 3.8 kilojoules per mole. And then a Gauss interaction between the methyl groups on positions 1 and 2. So that's another 3.8 kilojoules per mole. It gives us a total strain energy of 11.4 kilojoules per mole. On the right side, our molecule has 2 methyl groups. And if I draw this hydrogen in the back, I'm kind of drawing that funny, but we have to know that that's on that carbon, because not only do we have a diaxial interaction between this methyl group and that hydrogen, and this methyl group and that hydrogen, but also between the 2 methyl groups. Those are diaxial interactions too. That's a lot of energy. You can see that here, 11.4 kilojoules per mole. So let's put those on there first. So we have 2 methyl hydrogen diaxial interactions. Again, that's 2 times 3.8 kilojoules per mole. That's the methyl hydrogen diaxial interactions. Now we also have a diaxial interaction between the 2 methyl groups. That's 11.4 kilojoules per mole. And as we saw on the left structure, we have a methyl group here and this methyl group here, which are at a 60-degree dihedral angle to each other. It's a little harder to see if you try to draw that Newman projection, or rather a little harder to draw the Newman projection. But they're at 60-degree dihedrals. So we're going to add another 3.8 kilojoules per mole for that Gauss interaction from the table above. It looks like our total strain energy on the right side then is 22.8 kilojoules per mole of strain energy. So to address the question, it asks to calculate the difference in energy between these two. We would just simply take 22.8 and subtract 11.4, and so that difference is 11.4 kilojoules per mole. So the preference is certainly for the molecule on the left side.